In this session and this board, we still will not come to the crunch of the proof that the proof of the halting problem, proof that it's there's a particular language. We'll deal with the language, that particular language. We'll do it start with it this session, but we won't be able to prove that it's undecidable until we've picked up a few techniques, and so most of this board will be discussing one essential technique that we will use. This technique is called diagonalization, and it was invented. It's a fairly simple but quite ingenious technique invented by Cantor. That's George Cantor, I think German. Mathematician, lived over a century ago. He was concerned with infinities, different kinds of infinities. He's the one that showed that some infinities are actually larger than others. Like the infinity, I think I've mentioned this before, but the natural numbers, there's an infinite number of them, but that kind of infinity he labelled Lf0. And then he showed that there's a different kind of infinity, sort of, in a sense, a larger kind of infinity, and that would correspond to the number of real numbers. Now, obviously there's an infinite number of those, but that kind of infinity, the infinite number of real numbers, he called Lf1. And he's also famous for talking about the so-called continuum hypothesis. And that hypothesis is there's no other kind of infinity intermediate between Lf0 and Lf1. I'm not quite sure whether I got those numbers correct. The zero corresponding to the natural numbers, that's Lf0. And the infinity corresponding to the number of real numbers, that's Lf1. Continuum hypothesis says there's no other kind of infinity intermediate between Lf1 and Lf0 and Lf1. Right? Getting a bit ahead of myself, but so this board is essentially preparatory, essentially picking up the technique of diagonalization, how to use it, and then later we will apply it in the proof that a particular language, in fact it's related to Turing machines, that this particular language is undecidable, and we'll actually prove it. And as part of the proof will be this diagonalization technique that we'll spend this whole board on and more. So there's quite a bit of preparatory work to come. Alright, well, I can give you the language that we will show is undecidable. I can even give you the theorem statement, but that's about as far as we get. And then we branch off into the diagonalization technique, introducing what that is and how it works and so forth. But we start at least. So, okay, here's a language, and we're going back to machines now instead of grammars. We started with finite automata type machines, and now the M here, the machine here, is a Turing machine. Okay, more powerful again, more powerful than a PDA, and more powerful than a finite automaton. Okay, but back to machines. So the usual kind of thing. I've seen this sort of thing quite a few times now, and I suppose the earlier stuff, in a way, is a kind of lead-in to this critical language that with a few more boards we will actually prove to be undecidable. You cannot decide it. And what's the language? Well, it's the set of these ordered pairs, M, W. M's a Turing machine, W's a string, and the I've forgotten to close the brackets. Okay, it's a set. Yeah, language is a set of strings. So it's an ordered pair in the form of string. The angular brackets, as usual, means that that ordered pair has been encoded, has been put into string representation, and so the language is the set of these representations, these ordered pairs, and the condition, the property that all these elements of the set must have to be an element of the set, the description of the element, the property of the element, is that machine M, well, it's a Turing machine, M is a Turing machine, and that M accepts W. Okay, so any pair that's in this language, that's in this set, that string W will be accepted by the Turing machine M. Okay, that's the condition. Alright, well that language, and here's the theorem statement, that language, A suffix Tn, is undecidable. I'm not quite sure whether I should give the trumpet roll now or wait till the end of the proof. I think I'll wait till the end of the proof, because it's just a statement. It won't have any real emotional impact yet. But probably, well, I hope for your sake that it will, because it's really quite amazing, as I've said several times. Alright, well before getting into the proof, we can show at least that this language is Turing recognizable. I mean, it's not decidable, but it is Turing recognizable. And we'll show why that is. Now, can you remember the distinction between the two? A bit of revision. Turing recognizable. What does that mean? A language is Turing recognizable. That means that there's some Turing machine, there's some algorithm that will accept every member of that language, and it will reject any other string. Okay? No, wait a minute, that's a decider. Sorry. That is a decider. That language is decidable if what I've just said is true. Okay, now Turing recognizable, that's less powerful. A language is Turing recognizable if there is some Turing machine, some algorithm, which will accept all the members of the string, and that's it. Right? That's it. A decider goes beyond that. A decider can do what a recognizer can do, and more. And what it can do more is that it can reject all the other strings. Okay? A recognizer may not do that. So therefore a decider can do what a recognizer does. In other words, they both accept strings in the language. Okay? They both accept it. So that means that a decider is automatically a recognizer. You follow that logic? I've not, rewind. Okay, so at least we'll show that this language is Turing recognizable. In other words, we will show the existence, construction, proof by construction. We will show the existence of a Turing machine that will accept any element of this language, any element like that. Right? That's the definition of when the language is Turing recognizable. Alright, so this language is Turing recognizable. We'll show that in a bit later in this square. Okay, and if we assume this is true, we've only written down the theorem statement so far. I haven't proved it yet, but assuming it's true, then this this shows that recognizers are more powerful than deciders. Now, be careful. Powerful. What does that